Hi, good afternoon. Today's class we are going to see about demonstration of FIR filter with Python. Well, what should be the input signal and how your output signal, and what should be the cutoff frequency. For the current demonstration, let us assume that the signal with the below bandwidth, that is 1000 Hertz to 8000 Hertz. Maybe it has 1000, 2000, 4000, etc. up to 8000 Hertz or 1000, 4000, 8000 Hertz. Anything is possible within this band. So what should be the sampling rate for digitizing? What is the maximum signal frequency here? 1000 to 8000. So 8000 is the maximum sampling frequency. So what is it twice the maximum frequency? It is 2002 into 8000, which is 16,000 Hertz. Okay, it's right. Now let us assume that we would like to remove this 8000 signal, 8000 Hertz signal. We have number of frequencies and this one 8000 Hertz signal alone we would like to remove. How do we do all this in Python? So let us proceed. So what you need to know about is either you should do the coding in Google Colab or you can have your own Jupyter notebook with Anaconda or with your IPython IDE. Anything you can do that. So we will change the window here. Fine. So first what we are doing is minimum importing packages we are doing. Then we are going to create a signal for demonstration. What are the signals we are demonstrating? So since I already told you maximum signal is 8000, we are considering the sampling rate is 16,000. And let us take only the number of sample is 1000 for display, because otherwise it is so dense that you will see only the colored block. We will not see the signal. That is why I am taking n sample is 1 into 1000. You can change into many number and observe what is the change in the input and output signal display. Okay. So I said 1000 to 8000 Hertz. So we are considering 1000 Hertz, 5000 Hertz and 8000 Hertz signal. Amplitude is 1111. Okay. Fine. So as we said, the number of sample is 1000 and sample rate is 16,000. So what is the time duration? Because num samples divided by samples per second will give you the time. So that is T. We are finding out T. N we are finding out just because we want to do FFT. I'll give you that later. So signal first we have to construct. We don't know. We know that sine 2 pi f into t is the signal generation, where t already we found it with respect to number of samples and sample rate. So three signals, A 1 kilohertz, which is the amplitude of 1 kilohertz, A 15 kilohertz, which is the amplitude of 15 kilohertz, A 5 kilohertz, which is the amplitude of 5 kilohertz. All these things we have done it, and so that now we have created the signal by adding all the signals. By adding all the signals again, maximum frequency is 8 kilohertz. So next, what would you like to do? We are saving it in the wave format. In case if you want to listen to the sound you made yourself, wave file. The name of the wave file is test.wave. Okay, fine. So next, what we are going to do is we are going to see the FFT of the original signal. FFT we should is okay. First we will run this. Okay, so the next thing we can do, we can run it. And next thing is like we are going to see the FFT of the original signal, because after filtering and before original signal, that is before filtering, how does it look like? We should understand, because we are removing only 8000 kilohertz signal, right? So this is the FFT of the signal. The created signal is given as an input, right? The N is for FFT. It is founded from the first block. And these are all some plotting this thing only. So we will run it. Okay, what do you see here? FFT of the original signal. We have two different signal. What are all the signals? 1 kilohertz, 5 kilohertz, and 8 kilohertz. 1, 1, 5, and then 8 kilohertz also is there. Okay, maybe that amplitude is little down. We don't bother about it. Okay, three signals we have: 10,000, and then 5,000, and then 8,000. Fine. So next we will go. What is this? We have to design the filter, FIR filter. The design the filter in the sense designing the coefficients, where you will not give the signal as an input. Just we want to design the coefficients for the cutoff frequency. So what is the cutoff frequency we want to have? Because we want to remove 8 kilohertz, we let us give 6,000 as a cutoff frequency. Usually cutoff frequency in digital filter should be given as cutoff divided by Nyquist rate. So Nyquist rate is sample rate divided by 2. Sample rate already we have given as 16,000. So everything is there, and for number of coefficient is given as number of taps. So you are giving. So FIR coefficient is an array of coefficients. Array of 29 coefficients. Okay. Next, what we need to do is you should filter the signal. Now only filtering the signal. This L filter is filtering the signal. So FIR bin is the design of FIR filter. That is, it will give only, it will give us a return only the number of coefficients and the coefficient value, right? So this is L filter, which is used to really filter the signal. So the obtained FIR coefficient is passed here, right? And this one is signal. What is signal? Input you are giving as a signal. So here we get a filtered signal, right? So now let us give it to the FFT. We'll see what is the output of the FFT, right? So output of the FFT is two signals, only two this filtered. One which is 1,000 and 5,000. 1,000, 2,000, 3,000, 4,000, 5,000. Only 5,000 it is there. 8,000 signal is removed because our cutoff frequency is 6,000. Fine. Clear? So to demonstrate the FIR filter, what we have done is we have created the signal ourselves. After creating the signal ourselves, we are showing the FFT, that is frequency content in the signal. Already we know we have constructed the signal with the frequencies 1 kilohertz, 5 kilohertz, and 8 kilohertz, so that all the three should come in your FFT. All the three lines you should get, right? And after removing it, only two signals we have to get. Two frequencies we have to get. 8 kilohertz is the final one, so it is removed. Remaining two we have, right? So next part, it is just we want to see the input and output signal in time domain. Okay, so in time domain, pink is the original signal and green is the output signal, filtered signal. See the time 10 power minus 7, but here it is 0.0002, 000, maybe 10 power minus 3. Why is the difference? Because here 8 kilohertz signals also was involved, but here 8 kilohertz signal was not involved. See the gap also between two lines, it is much little difference only you can see, but with respect to x-axis we can see clearly that this is the pink is the input signal and green is the output signal. So you can save the filtered signal also in the wave format, and you can listen to both input wave file and output wave file. And if your ear so nice, so choosy, and it could differentiate between the removal of 8 kilohertz signal and with the 8 kilohertz signal. Thank you.